Hello. Today we're going to talk about the basic concepts of digital images. We are going to be discussing 8-bit grayscale images, 8-bit RGB images, and 24-bit RGB images. We will also be talking about histogram and equalization of images. So let's start with how an image looks like, digitally speaking. An image is just a matrix consisting of rows and columns. And each of these little squares are called pixels. This is a pixel, this is another pixel, this is another pixel. And a pixel is represented as a coordinate depending on which row and column you find it. For example, this one here, 86, Pixel 86 is found at row 2, column 8. That would be the pixel location. So this is how it is represented basically. And if we go further, we have 8-bit gray level images. These are basically encoded pictures of pixels on grayscales that go from 0 to 255, where 0 is completely black and 255 is completely white. And the numbers in between represent different levels of a gray scale. For example, if we have a 640 multiplied by 480 8-bit image, this means 640 wide, this is 640 wide multiplied by 240 high, right? This is width and this is height. So in this case, this image would be around 300 and 307.2 kilobytes for size, right? We need 307.2 kilobytes to storage this image. So this is an example of that image. As you can see, it is not as clear as we would want it to be, but we can still see what's showing up in the image. We can see here there is like a boat, maybe some cars. I don't know if it is a boat or a building. It looks like a cruise. So this is the way images, 8-bit images are represented. And on the contrary, 24-bit color images consist of three elements. One, let's say one group of red tones, that is why we call it R. One group of green tones, green scale, that is why it's called green, and the other one is called blue because we have a blue scale here, right? So we have three components encoded in 8 bits, each of them. That's why we have 3 times 8, it gives us the 24-bit image, right? So it is something similar than with the gray scale, but in this case we have three different scales, a red one, a green one, and a blue one. So we need all of this to form a complete full color RGB image. And we can have like 224 multiplied by 16. It gives us like, um, sorry, here the number is not good. Don't pay attention to this number. I'll tell you the right number in a minute. Don't pay attention to that number there. The actual number when we talk about a 24-bit image is something like Let me show you. Wait a second here. It's this one here. We have like 2 elevated to 24. That gives us like 16.777 to 16 uh, by 10 at 6 at the power of 6 different colors, right? A 640 by 480 for 24-bit color image requires like 9 uh, 921.6 kilobytes for storage. That's why they are heavier than the black and white images, right? Or the grayscale images. So in this case, um, well, we have um, encoded this image. It's the same, it's just a matrix, but on each pixel we have three um, different elements, right? And finally, we have some alternative to these 24-bit color images. We have also a matrix, but the matrix do not contain the color values here. They merely contain pointers that address to a different file, which is a color indexed image that contains all the numbers that are required on each one of the pixels. For example, pixel number 5 goes to this number in red, which is 66, to this number in green, which is 132, and to this one in blue, which is 34. So this way we have everything encoded, but usually they are uh, less heavy than the 24-bit color image. So, for example, a 640 multiplied by 480 8-bit color image requires the same amount of kilobytes, 307.2, for data storage. It's the same amount of kilobytes that we require for a grayscale image. But we need also um, three uh, three times three elements of 256 multiplied by 768 bytes for the color maps, right? So that's the other thing that we need to encode properly these 8-bit images. Basically, with today's computers, we don't have any problem to work with 24-bit images. Okay. Sometimes we need to compress a color image to a grayscale image so we can save in or we can economize in computer resources. Um, and we change the colors into another matrix. The color matrix, we change it into another matrix that is called YIQ. It is an acronym where Y represents the luminance, um, the I channel represents the in phase, and Q represents the quadrature chrominance to represent the color details. And basically, it is converted by multiplying the RGB matrix to these other matrix with fixed scalar values. And um, after we transform our RGB image, we can uh, we can change it back to what we had before with a less resolution, let's say. So we usually do it by uh, computing this equation here. Okay, and then to obtain a grayscale image, we convert each RGB pixel to an YIQ pixel, and then we discard its IQ chrominance channels because we don't need them. Basically, most of the information is kept inside the y vector. So the y vector is represented by this amount of the red, green, and blue elements inside the matrix. So this is the way it is performed. Theoretically, obviously, I mean, in practice, we will do it using MATLAB. And well, finally, we need to see how the how many pixels are contained on each scale level. And to do that, we need to see the histogram of an image, which is something like the frequency response of an audio file, of a sound file, right? But in this case, all these elements represent the levels of color inside these these bars, right? For example, the pixel 0, we have 2 pixels because we have like 2 levels of this, let's say, gray level, right? In pixel 1, most of the grays are contained inside this level, right? Most of the picture contains a lot of this type of gray, let's say. Some of it, and a little bit less of these other elements, right? So basically, we need this to equalize an image. We say equalize because we tend to make these different levels, um, somewhat similar to each other, right? And that's the way the Photoshop and all these software programs work, by changing the intensity of pixels inside each one of these um, levels, right? So the more pixels I have on one of my levels, the more color, or the more luminance of this color we have on an image. I'm going to show you some examples of it. Let's go to MATLAB. Don't worry, I have already covered here. This is the code I used to create the different histograms for this image that we have here. So first, I'm going to show you the grayscale image. As you can see, this is the grayscale version of this original photograph. In this version, you can see that most of the black levels are, um, I mean, we have a minimum of these levels, these black levels. We have like 2000 pixels containing levels of black, and most of the colors are contained inside the, let's say, wider wider side of the spectrum. So these are basically the result of this light around the picture. So this picture is lighter than darker, right? So this is the element, the histogram for this picture here. Now I'm going to show you the histogram for the grayscale domain. I mean, if we change this into grayscale, we have more or less equalized histogram. Here you can see that it is almost normalized. Most of the levels are normalized to 8,000 pixels for each level. And this other image, which is the color version of the image, as you can see, it's more similar to the one in black and white here, right? They look alike a lot, except that because we are talking about the luminance here, luminescence, sorry. So the lighter it gets, it is the same if we see it in black and white or color. Basically, we have the same response, let's say, the same histogram. So if we check the white channel, the luminescence channel we talked about earlier, you can see that it's almost normalized. The energy is contained inside this channel, as I told you before. It is almost normalized. And then we are going to see the RGB channels. In this case, we have, well, more or less kind of a balance between the left side of the spectrum and the right side of the spectrum because, well, this is a balanced image. We have the same amount of dark color and somewhat lighter colors on the bottom of it. And finally, this is an indexed version, an 8-bit version of the picture. Remember that the 8-bit version tends to be uh, lighter than the 24-bit version, but look at its histogram is not as balanced as it was when we encoded with. Sorry, let me show you again. When we used, no, not this one, but this one here. I mean, it's not as balanced as this one. So we can see that somewhat 8-bit images tend to be poorer in terms of their quality, right? So that's basically it. Um, we will check on our next class some details of these concepts, and we'll go in depth into the MATLAB code. But we can stop for today. So see you each other on Monday. Thank you very much.